Today, I'm going to be going through a project I've been working on for the past 3 weeks about how to simulate a live active network. This project is divided up into 3 different sections. So if you want to skip ahead and see the other 2 parts, you're more than welcome to do that. But I'm going to be going through this video from section 1 to section 3. And the first section covers a protocol called Go Back End. Now, this protocol is a layer 4 transport layer protocol that allows data to be sent from one node to another. It is a sliding window protocol, meaning that data is sent one packet after the other in a specific order. So this prevents randomness amongst the data as it's being sent. So if you want data to be sent in a particular order, this protocol is going to allow you to do that. Now, you can also go to this simulation here and see how it works for yourself. I'll put the link in the description below. But basically, if I start sending packets out, you see that they are being sent in a specific order. The receiver is acknowledging it in a specific order. And every time the sender gets an acknowledgement, the window moves forward. In this case, the sequence number 3. You can also drop packets. So if I want to kill a packet here, the receiver will say, hey, I never received packet 3, and the window in this case won't move forward. And you can mess around with this a little bit more, but generally you'll see that after some time, the packets will be retransmitted. So it takes at least 20-30 seconds for it to get the timeout to happen. Yes, it happens now, and then the window moves up to 6. Now, in my simulation for Go Back End, what you can do is follow these instructions here, and I'll explain each of them. For starters, you definitely need a Java GBN node, and a sending port. In this case, it's 5000. Receiving port, in this case, is 5001, and these can be like 1000, 2000, just whatever you want, and definitely a window size. So in this example, it's 4. In this simulation here, it's 5, but really it's whatever you want. Now, these other 2 parameters is the drop rate. So you know how I used to drop packets here. So if I send a packet out, slower, of course. So if I send it, yeah, fine, we'll just kill that packet. That's basically what the drop rate is simulating. So if I do /d and then 2, that's basically saying drop every 2 packets no matter what. So if I wanted to drop if I set this parameter 1, then I'd be saying drop every packet and nothing would ever get sent, which in this case, you don't want that. So just leave it at least 2 if you want to simulate a network that actually works. You can also have a probabilistic drop rate by doing /p and then assigning a decimal value between 0 and 1. So if I have a float of 0.1, that's basically saying drop 10% of the packets randomly. Now, going through the examples down below in the README file, I'll go through the first example here. So if I do Java GBN node 2000, 1000, I'm not going to say 4 1s and then 4 2s. If I do that here, you're going to get a prompt, but you also need to enable it on this side too. So if I do Java GBN node, this is saying that 1111 is the receiving port. So here it has to be the sender. And then if this is the sender port on this side, this also has to be the receiver. This window size can be different. So you can do 4 or 3, whatever you want, because these 2 windows are considered their own separate clients. So you can actually just put this as 3 /p 0.1. That's saying drop every 10 packets. And now I do send A, B, C, D, E, F, G, H. And you're going to see here that this client is sending packets out to this node. And this window is sending acknowledgements back. So I know it's not 10% here. But if you keep messing around with it, IJK. So I'll just add more examples. So you'll see that like duplicate acts were received, and it's slowly converging to 0.125. So this is 0.07, and this is 0.125. So it's approaching 10%, which is what we assigned here. There are other examples, more interesting cases, where you can have packets be sent forever. So if I decide to do, so if I try to terminate that window, 2000, 2001. And then you decide to do like send NAT. You're going to be caught in an infinite loop here, because what's happening is that when I scroll up, you'll see that this packet gets sent to a receiver, acknowledgement gets sent, and then this sender sends out A, but you're telling the node to discard every 2 packets. So I'm going to be discarding packet A, and then this will start receiving duplicate acts, and then this node constantly sends packet letter A and packet letter T, because this gets broken down into characters. So for each character in the string, it gets broken down and then sent over to the receiver. And then the receiver is saying, well, no, I am supposed to drop every 2 packets. So you get caught in this infinite loop. So that's how it works. You can do a couple other things. Like here, for example, if I decide to do, you can actually have both drop rates working at the same time. So if I want to do 3000, 3001, and I want to do window size of 5, drop every 2, and a loss rate of 1/2, meaning you'll drop 50% of the packets, which is a very large amount of packets. I have to add the 5. That's the window size. And then I do screen share, just like that. You can see that this is sending out 5 packets at a time, which is the window size. And you can still see that this is going. And it might be caught in an infinite loop. I'm not too sure just yet. No, it's not being caught in an infinite loop, but you can see that's going to take a while. And then you get these very interesting cases where you're being told drop every 2 packets and you have a loss rate of 50%. Well, that makes sense, because if your loss rate is 50%, you're going to be losing a lot of your packets. And then you're saying drop every 2 packets, and that just causes a mess for the network. So realistically, you wouldn't want to do something like this, but using Go Backend, you can see how your network is going to operate over time. So the next step to emulate the live network was to figure out a way to have the routers identify the least error-prone routes from one client to another. And the way I decided to do that was by implementing what's called a distance vector protocol algorithm. You may hear me refer to it as DVP for short. The DVP algorithm is a dynamic routing protocol that calculates the best paths for sending packets between network nodes. It uses Bellman-Ford computations to calculate the shortest path and relies on periodic changes of routing tables between neighboring nodes to update the routing information. So if you have a network that's trying to send something from A to B, and the direct link is very error-prone and it just doesn't work very well, you can possibly get around that by using a more efficient link. So DVP basically says, okay, I'm going to find that link for us. Just to give us an illustration of how this works, we see here an example of this distance vector in action, where you have 9 clients, all of which have their own routing tables. Now let's look at A here and just what this table represents. When you see DAB equals 8, that's saying the cost of the link, the cheapest link from A to B is 8. And if I have a cost of infinity, that's saying, okay, well, I don't even know. So like in A's case, A is saying, well, I don't even know C exists. Technically, A doesn't know that C exists. But if I look at A to D, I see that there is a direct link, like A knows D exists currently. So it just says the cost from A to D is 1. So obviously, there is a much less, well, there's a less error-prone route between A and B. And that's why going from A to D, D to E, and E to B. And that cost is 3. But right now, A doesn't have that information. It says the most cost-effective route from A to B is 8, when it should actually be 3. So that's what DVP actually resolves, is that eventually you're going to have all of these routing tables and all of the 9 clients to have the cheapest routes and the least error-prone routes. Every time I say cheapest, I really mean like the least error-prone or the least likely to lose packets. So eventually all these routing tables are going to have those updated weights so that the network can send packets effectively. So when I look here, basically DVP, all of the routers are sending information to one another. And then it's performing this computation to get the least error-prone route. So when we saw infinity values up here, basically these values, these infinity values are going to become actual numbers. And so when I said earlier, like from A to C, it's infinity, meaning that A doesn't know C exists. Eventually, A will know that C exists. And it will know that by giving an actual number within the routing table as opposed to infinity. So that's what that computation does here. And then realizing that that these routers, that there's more routers than what they originally thought, it's going to resend the routing tables, and it's going to update costs, try to get the cheapest link from one client to the next. So you see it's doing this again and again, and this will take many computations. For a network this long, it's going to take a while. So this process is just going to continue. Now, to show you how to implement DVP using the code that I have on GitHub, we're going to use this sample example of a network. I found that using letters was easier to denote the network, but instead of using A, I'm obviously have to assign these numbers. So A has source port 1111, B has source port 2222, and so on. And the numbers I have here, 3245, when I implement it in code, it's actually going to be 0.3, 0.2, and 0.4. I think you'll get the gist. Now, if you look at my GitHub, you'll see you will see a very confusing syntax here. Might not make any sense. I understand. I'll go through it just in a moment. Let's assume this terminal here represents client A. Obviously, you need Java DN node to start off. And then insert the source port, which in this case for A is 1111. And then you get all of the neighbors. So in this case, it's B, so it's 2222, and then the loss rate. So they're saying that this has a 30% chance of losing packets along this link. And then that's it, you're done. Now, I know in this example, it is a directed graph, but when you have a network, at least in this case, you have this works for undirected graphs. So even though this picture here shows a directed graph, the thing I have is for undirected graphs. So when I have a source port of 2222, I would basically also I would get the connection from B to A, 1111.3. Then from C, from B to C is 3333.2, 4444, which is D, and then it has a loss rate of 0.4. Basically, what I'm doing, these 3 source ports are neighbors to B. And that's why I'm including the loss rates here. Just to show you what I mean again, let's assume this window is for client C. And now I have that source port 3333. And then I get all of the neighboring connections. Again, these are neighbors to client C. Now, in this example, and just generally, whenever you're done creating the nodes and you have your network set up, you need to add this last keyword so you can tell the distance vector protocol algorithm to actually start this process of computing the least error-prone paths. You need that last keyword, because if you don't have that last keyword, you're going to be telling the network that you have more nodes to add to the network, which is not what you want to do. This last keyword tells you, I'm done building this network. Now implement DVP. And after a while, actually, that took no time at all. I mean, basically, you could see that it computed it very quickly, that it didn't need any time at all. So you can see, if you can go through this example, it's in the GitHub, and you'll see that this actually produces the correct numbers. Like from A to E, the cheapest link is 0.3 plus 0.4 plus 0.2, so that's 0.9. Again, this is an undirected graph, not a directed graph. And you'll see from A to E, it's 0.9. Originally, the calculation was wrong because it was sending routing tables. But eventually A realized that, hey, this information up here is wrong. Let me recalculate. And then that's what this is doing, basically. So you can go through all of these and you'll see that the information is right. I've checked it a couple times before I gave this video presentation, and it works. I ran out a couple other examples as well, so you can do some testing, see how it works for you. And I understand that this works only for static networks. That was one thing I was looking at when I was implementing all of this. And I understand for live networks, these links are constantly going to change. And so in the next section, I have code that will deal with that problem. And every time you have updated weights between these individual routers, you'll be able to implement DVP to reflect those changes within the network. So hope you enjoyed this, and we'll move on to the next section. I'm going to be using this example of a network to show you how loss rates can be computed in real time. So if you look here, you'll see there are 4 routers, each of which have their own error rates associated with each link. But in reality, we don't know the loss rates between each node in a realistic network. Like when we start out with 4 clients, we don't know the probability that one link will fail to deliver a packet. We just don't know the chance of that happening. And so originally, these are all like question marks. Like we don't know what these values in this picture are. Like they're just all question marks. And so what you have to do is you'll see that port 1111 sends packets out to 2222 and 3333. And the idea is you're just going to flood the network with packets and try to figure out the loss rates. Because if you have so many packets getting sent out, the idea is that you'll have a good idea of what the loss rate is going to be after sending like maybe 1,000 packets out at a time. And you'll be able to generate these values here within the picture. Because if I send like 1,000 packets from port 1111 to 2222, and I see that 100 of them get dropped, that means 100 out of 1,000, well, that's a loss rate of 0.1. And so that would be how you get this value here. And similarly, from maybe port 1111 to 3333, if I send out 1,000 packets and 500 of them get dropped, well, that means you have a 50% loss rate, and that's where you're getting this number from. And so that's how these loss rates get computed. But that seems like a whole other process in and of itself. But actually, my solution bases that off of the go back end protocol that I showed you a little bit earlier. So if you look back at the GitHub here in the README, and you look at Java GBN node, you'll notice that there's a loss rate associated here. And that is going to be extremely valuable in getting the loss rates that are within this picture up here. So if I have like a loss rate of 0.08, that's actually very close to 0.1. So it's just similarly like you'll actually be able to take that loss rate that I just showed you in GitHub and apply it to this link here.
in this example. And you're able to do a couple other things here. Like you see this one has a loss rate of 0.4. This has a loss rate of like 0.44. This one doesn't have a loss rate at all, which is a good thing. And so you get the idea. So if I use go back N to generate these error rates, DVP is then going to disseminate those loss rates to all of the clients, so each router can compute the least error prone, aka the cheapest links. And so to simulate this loss, obviously everything's being run locally. So you need to give the clients some way to just drop packets. And so the idea is the receiving end is going to be dropping packets just to simulate what this would look like realistically. And once the sender recognizes that some of the packets get dropped, it's going to calculate this loss rate using go back N, and then DVP is going to disseminate that throughout the network. And eventually these loss rates are going to converge to the ideal values within this diagram, so the clients can determine the least error-prone routes from one router to the next. So to show you what I mean by that, this is like an example of this successful convergence of like port 1111's routing table. So like this is like where it started, and then like after some time, you know, just obviously this is where it began. Like you'll see here from 1 to 2, this had a loss rate of 0.14. And after some time, the loss rate became 0.11, which is very close to 0.1. And then it got down to 0.08, which is also okay because it's very close to 0.1. Again, this is all being probabilistic, so it's not going to be exactly at 0.1 or 0.2. But it will be around that number eventually. So just to show you how this works, also, if I look at node from going from 1 to 4, you'll see that this is 0.81, which actually makes sense. Because if I want to go from 1111 to 4444, I'm going to do 0.1 plus 0.2 plus 0.5 to get from 1 to 4. You can see you might be able to see my arrow here. And that gives you 0.8. And then it turns out, looking here, that's 0.81. So it's practically identical. It's not going to be exactly on 0.8 just because it's probabilistic, but you get the idea. So now to show you what I'm doing here, this syntax might not make sense, but again, I'll show you how it works. So if I take this example here, you're going to start with Java CN node, and then you're going to type in receive. So we're going to be looking at port 1111 in this example. So I look at the syntax. You take your local port 1111, and then you're going to be looking at all of the receiving ports. So you're going to notice in this case that 1111 doesn't receive packets from anyone else. So you're going to leave that blank. But you notice here, based on the arrows, that you're sending packets out to 2222 and 3333. Because you're going from 1 to 2 and 3. Just to show you here again, I'm going to be looking at port 2222 now. And I received packets from 1 with a loss rate of 0.1. And I send packets out to 3333 and 4444. Show you here. Port 3333, I received packets from 1111 with a loss rate of 0.5. And I also received packets from 2222 with a loss rate of 0.2. And I also am sending packets to 4444. I think you get the idea. I have a C from 3333, 0.5, 2222 with 0.8. And I'm not sending packets to anything, so I just leave that blank. But I also have to be sure to add the last keyword so this whole process can begin. So always be sure when you're done creating the network, you add the last keyword. So now that everything's running, you'll see that it may take a couple times for this to work, just because of how the probabilities associated with each link are the way that works. it's going to be a pure randomness, so it may take a few times for this to actually give us the desired results. But you see here generally that the loss rate from 3 to 4 is like roughly around 0.5. And you'll see here that this loss rate is around 0.2, from 2 to 3, and from 2 to 4, the loss rate is about 0.8. So it's going to take a full minute for it to work, maybe more, but we'll see how it turns out. So I'll just let it sit here, see what happens. Now you see the routing tables are starting to be sent out. Generally across most of them. It's okay, they're not all being sent out just yet, but eventually you'll see a lot more changes. All right, so generally you can start to see everything coming together now. If you look here, this is node 1's client table, and you see the length from 1 to 4 is generally about 0.8. Right now it's like 0.79. With the diagram, the theoretical result should be 0.8, but that's okay because we're off by like 1/100th, which is okay. You also look at node from 1 to 2. The loss rate right now is 0.14. The ideal should be 0.1, but again, this is all probabilistic, so that's okay. We're only off by a couple hundredths here. You go up, you'll see that's about 0.1. And again, from nodes 1 to 3, the ideal loss rate should be 0.3 because it's 0.1 plus 0.2. But then here's about 0.32. Again, that's okay. Not off by much here. So yeah, we can let this go for a bit more. But I think you see the point that generally these loss rates are what we expect from the network. And because DVP is probabilistic, you're not going to get the exact values, which is okay in this case. But I think that explains how this network works. And I'm sure you can apply this using a couple other examples and you'll get similar results, but just give it a shot in your own free time and I'm pretty sure it'll work. So thank you again for watching. And if you have any other questions, you can look at the GitHub. This will all still be there. If you look at the GitHub, you'll see the test cases of everything I'm doing. It's all documented, so you won't have to worry about that. If you have questions, you can also look at the code. Everything's divided up into the folders here again. Just check it out on your own free time. So again, thank you so much and have a great rest of your day.